Bertrand from INRIA, who will tell us how to control probabilistic systems under partial observation.
Okay, thanks. So first of all, I'd like to thank the organizers of this workshop for giving me the opportunity to give this talk, and also more broadly the organizers of the program for inviting me. So I'll be staying here a month, so all of October. So this is in this talk I'd like to introduce one of my research topic. And yeah, if you see connections to your work, or if you're interested in some problems I'll mention, then I'll be happy to discuss them further during the month of October, or later. Okay, so in this talk I'll try to give some techniques, or at least some rather well-known results about controlling probabilistic systems when you only partially observe them. And for this, given my background, I'll take an automata or verification approach. So it might be different to what some of you would do in their domain. So the talk will mainly survey some existing results, but also give a few open questions and discuss some research direction I'd like to investigate. So, first of all, why am I interested in that problem? So, why probabilities? So maybe this is a slide that you will all agree with, I hope. So why probabilities? Well, probabilities are very convenient if you want to model randomized algorithms, for example. And we know that randomized algorithms are needed to solve some problem that deterministic algorithm cannot solve everything. They can be used also to model some unpredictable behaviors. It's quite convenient when you don't know exactly what will happen to quantify over the possibilities using probabilities. And very similarly, it can also be seen as an abstraction of non-determinism. Okay, now why partial observation? So in my opinion, at least, that there could be two different motivations for that. So the first one is that if you have a huge system, then it's very unlikely that you can describe it with high precision, and you might want to, in order to describe it, you might want to forget about some details. And if you forget about some details, it basically, so maybe you forget about some values, the values of some variables or stuff like that, and this pretty much amounts to having only partial observation of the state of the system. So this first reason is, yeah, maybe the system is just too large. You can describe it very precisely, very accurately. The second reason can be something that you wish, unlike the first motivation, and namely, for security concerns, it might be good, but that a user doesn't know everything from the system they are using. So if the user is an attacker, then you would like to prevent the attacker to know everything that's going on in the system. Okay, so in this talk, I will consider models that combine probabilities and partial observation. And these models are some extensions or some variants of automata. So here I depicted two examples of such models. So maybe let's start with the one on the right-hand side. So maybe colors are not very visible, but with this cloud, what I want to represent is that an attacker or a user cannot distinguish the three states 1, 2, and 3. Okay, so this is not, the user will not be able to distinguish in which state the system is, whether it's 1, 2, or 3, but it will be able to know whether the state is W or L. On the left-hand side is another example of partial observation in which what I mean by this is that the user will not distinguish, will not see all events, all actions that happen, and some of them won't be visible. So these two actions will not be visible to an external user. Okay, so we will have such models like automata and with partial observation. I cannot see the precise state of the system, or I cannot see all the actions that happen in the system. And for all this talk, still the attacker or the user will know the model. So it will know that the system is executing that particular model. Okay. So on such models, we can ask several questions. So first of all, we can start with language theoretic questions. So probabilistic automata are an example of, I will develop that, but probabilistic automata are an example of a model combining probabilities and partial observation. And you can be interested in defining languages that are recognizable by probabilistic automata. Another kind of problem is monitoring. So if you only assume that you passively observe the behavior of the system, what can you deduce from your observations? So maybe you would like to be able to diagnose that fault occurred in the system, or maybe you want just to supervise its behavior in order to know what has been going on more generally. Okay, and the last possibility, which we will be focusing on in this talk, is the class of control problems. So here you assume that the user or the attacker is active and can interact with the system. And more specifically, the objective of the user will be to optimize some quantity for a given objective. Okay, are there questions so far? So please do not hesitate to interrupt if there are questions. Yes.
When is that Q and L? Is that
okay? This was okay. This stands indeed for winner and lose.
These are just normal states?
Yes. Okay. These are just states and that one can observe.
Maybe you said, but I didn't understand. How is it specified what is observed and what is not observed? Is it part of the specification of the automaton, or is it on the run? I mean,
it's in the model, and so mostly in the rest of the talk I'll be studying this kind of model in which you don't observe the precise state of the system, but you observe, let's say, an equivalence class. So maybe when the system is in state 2, you don't know that it's in state 2, but you observe that class, 1, 2, 3, and yeah, no more. So for, okay, maybe we can go through that example. If initially the system is in state 1, and then the user executes, and okay, action A occurs, then the observation would, in state 1, 2, or 3, will be the same, just because it's confused with these three states. And so the user wouldn't know whether the system is in state 1, 2, or 3. Okay? So this is what this cloud represents. And the objective, in that particular example, the objective for the user is to go to the winning state. But since they don't know whether the system is in 2 or 3, then they won't be able to play, let's say, action B or action C, because it would be losing for one of the states. So sorry, I did not necessarily want to go into more details on that particular example, but yeah, mostly we'll consider models in which you have equivalence classes on the state. Okay.
On the left-hand side, when you described it, you were saying that you can't see certain actions, so that seems a bit different from...
Yeah, so on the left-hand side, indeed, it was different. The idea is you just observe events, so you just observe letters, but you don't observe all of them. You don't observe those that are in clouds.
So it's not a quotient like this one, it's not an equivalence class.
No, but you can, in fact, you can transform into the other model. Yeah. Okay. Okay, so this was the motivation for studying systems with probabilities and partial observation and trying to control them. So I'll start with a quite old model, the one of probabilistic automata. So it's different from probabilistic automata, I think, that Frank mentioned in the morning, which were Segala's probabilistic automata, and here are probabilistic automata by Rabin. So a motivating example for probabilistic automata is the one of a planning control, a very, very simple planning control. So imagine you want to plan your holidays, your next holidays, but you'd like to plan them in advance. So you'd like to, before leaving your home, you want everything to be settled. So the first thing to do is to choose, an airline and maybe an airline type here, so either low cost or high cost. And then you can book, once you have your plane tickets, you can book an accommodation, and this you could do over the internet or by phone. And then once you choose your accommodation, you might be interested in choosing a tour, and this could be I want to see all or to miss nothing. Okay, these are two options, and we assume here that each action may fail with some probability. So this is how I represent the let's say the problem. So we start here at home, and then we chose either a low-cost company or a high-cost company. If we choose a high-cost company, then the probability 1 will make it, let's say the plane is more reliable and will make it to the airport because the plane will indeed depart from the origin. However, if you choose a low-cost action, then low-cost airline, then with some probability the plane will be cancelled and I won't be able to make it to my holidays. This is very subjective, but you can instantiate with different names here. Now, when we reach the airport, and depending on whether we booked the accommodation on internet or over a phone, then again there could be a problem, and maybe you don't make it to the hotel, and so on. Well, I think you understood the semantics. And given a plan, so a plan is just a sequence of choice. So I choose an airline, I choose an accommodation, how to book the accommodation, and I choose a tour. What is the probability that it succeeds? And by succeeding, I mean going to this success state. And you can compute it as a product of probabilities. And maybe if there are several paths, then you need to sum up the different paths. So why is it a partial observation problem? Well, it's really because you need to plan in advance. So you need to give the whole plan before leaving. Okay? You don't know what will happen after the first step, and so you start and you don't know whether you'll be at the airport or in the failed state, but still you need to decide your second action. Okay, so as we see the control strategy, there are really words. So you say what I'll do in first step, second step, and so on. And you can wonder for each control strategy, what is the succeeding probability? So what is the probability to reach the final state or success state after some word? So here is how we can compute it. You can think really of it as a product of the initial vector, initial distribution over the states. Then this is the concatenation of all individual matrix for each letter, each action. And here you have the final vector. So which states are final? Just 0, 1s. Of course, you'd be interested in optimal strategies, but as Martha mentioned in the morning in a different setting, optimal strategy may not exist in general, so it's very easy to see that, for example, on this example, if I... so we initially start in Q0 with probability 1, and assume you want to reach Q1. So one good way to reach Q1 is to choose action B, because B can lead to Q1, okay? But you can see that it only leads to Q1 with probability 1/2. So of course, if you play a long sequence of B's, then you'll increase the probability to reach Q1, but you'll never, I mean, you have an increasing sequence of probabilities, but you'll never reach 1. So there's, on that example, there is no optimal strategy. Okay, so given that there are no optimal controlling strategy, we may wonder, I mean, another objective could be to find good enough strategies. So strategies that ensure some probability level. So how to specify that? Then, well, you can define the language of an automaton as, so given a threshold theta and some comparison operator, as a set of words such that their probability agrees or meets that threshold. Okay. Unfortunately, the problem, if you're given a probabilistic automaton, of telling whether such a language is empty, or non-empty, sorry, is undecidable. So this is a result by paths. already a few decades back. So this essentially means that you cannot tell whether there is a good enough strategy. Okay.
It's surprising.
It is surprising, yeah. Yeah. So, just to go a bit further, this undecidability result is somehow robust. Why? Well, you can refine that non-emptiness question. So, for example, if you assume that you start with a very specific, a probabilistic automaton with a very specific property, and what is this property? The property is that either some word is accepted with high probability, so greater than 1 minus epsilon, or all of them are accepted with very small probability. So you already know some kind of separation property. Not really, but then you cannot decide, it's undecidable to tell which is the case. Okay? So this is very strong. It means that, at least in my opinion, it means that the undecidability is very robust.
But do you know what the epsilon is, or are you just told there is one?
You're given, even if you're given epsilon. Yeah, it sounds crazy. So you could think, okay, but maybe this is because you're not playing on the threshold and the precision of the threshold, and so by threshold I mean this 1/2, and this is what makes everything difficult. But if I don't take 1/2, but if I take 1, is it easier? So here I ask maybe a slightly different question, which is, as in the example I had before, so does there exist a sequence of words such that the limit of their probability is 1? So can I get arbitrarily close to 1? And this problem quite recently was shown to be undecidable as well. So it's not only very specific quantitative questions are undecidable, but also qualitative ones. And then it was, so this second undecidability result was refined by Nathalie and others. So if the automaton you're given at the beginning doesn't have real probability values but parameters, so just parametric probability values, and if you ask whether there exists a valuation of these parameters that makes this property hold, so value 1, or if you also ask whether all valuations make that property hold, it's still undecidable. Okay. So this can be considered as rather bad news because somehow you cannot decide whether there are good enough controlling strategies. Okay, so is anything decidable? Yes, there are a few decidability results for probabilistic automata. So if you do not consider value 1 problem, but if you ask whether there is some word accepted with probability exactly 1, then this is decidable, and it's a p-space complete problem, and it's basically equivalent to the, not basically, it's equivalent to the universality problem for non-deterministic finite automata. So why is that? So if some word is accepted with probability 1, finite word, this really means that all computation of that word end in some accepting state. So if you take the complement of the accepting state in A, it's the same as the complement automaton is not universal. Okay, another question which seems at first close to the emptiness problem is decidable. So what is this problem? It's the quantitative language equivalence. So you're given 2 probabilistic automata, and you ask whether for all words they give the same acceptance probability. So this problem here, so it's much stronger than asking whether the Boolean languages are equal. You really ask for the quantitative languages to be equal. Then this problem can be decided in the polynomial time, and it can be seen as a consequence of some more general result by Schützenberger, and was later rediscovered, or at least proved in that particular context by Zhang. And the arguments used there are just linear algebra arguments, and the proof gives a bound which is polynomial on the length of, if the equivalence doesn't hold, then you have a polynomial bound bound on the length of witness that the two languages are not equal. Okay, so this is time remaining, right? Yeah. Thanks. Okay. So to recap on that part, and I'll try to be a bit quicker on the second one. So again, in probabilistic automata, there is some kind of partial observation because the plan must be decided in advance. The model of the system is known, so if you choose a plan, if you choose a controlling strategy, then you can pre-compute what will happen. You can compute the sequence of probability distribution over states that you'll have after each step. However, this is not sufficient to get decidability of most optimization problems. Okay, so in the next part, I'd like to extend somehow the model of probabilistic automata with the following. So if when you execute a plan, you have some feedback of what happens in the system. And you're able to modify the plan depending on that feedback. So we'll come to a model that probably most of you know, which is the one of partially observable Markov decision processes. So it's the one I will present is a very specific subclass of it. I still call them partially observable MDPs. So an example of a problem in which POMDPs can be used is a variant of McCallum maze. So you assume that you have a robot, so that has limited sensor abilities, and also its moves are imperfect. So what do I mean by this? So you have a maze, which is represented here, and you have here, I don't know how many cells, 10, 11 cells. And you assume that when the robot is in this maze, and it can only see which walls are surrounding it, but not the precise cell. So maybe it sees, so for example, here in that upper corner, it sees that there's a left wall and an upper wall. And in that cell, it sees an upper wall and a down wall, and so on. Okay? So it cannot distinguish that cell from that one. And okay, it cannot distinguish either of those three cells. And what are its actions? So the actions are to move north, west, south, or east, but we assume that they're not implemented in a very accurate way. So if it chooses north, then it will go to north with probability 2/3, and maybe in the other possible directions with other probabilities. Okay, so here the observations the robot receives are really the walls, so those tuples, but not the precise cell. And the objective, so initially the robot is placed arbitrarily on the grid, and the objective is to reach that target cell, and also to optimize the number of steps towards reachability. Okay, so now what are strategies in such models? Well, strategies really map histories of what has happened so far, because now you can update your plan depending on what happened. So what has happened so far is a sequence of actions and observations. So actions is A and observations are omega, and it maps it to a distribution of our possible actions. Okay, so we'll distinguish two kinds of strategies in the sequence. Pure strategies, where here you don't have a distribution, but you have just an action. And what here I call belief-based strategies. So what I mean by belief-based strategy is a memoryless strategy. So it only depends on the current set of possible states. Okay, it does not depend on the whole history, but just on the set of possible cells, let's say, the robot is in. Okay, so what is this comment here? Yeah, okay, so the link between POMDPs and probabilistic automata. A word in a probabilistic automata exactly corresponds to a pure strategy in a blind POMDP. So by blind, I mean that the observation is always the same, independently of the state. So the set of observation is a singleton. So as a consequence, all the hardness results we had for probabilistic automata, they lead to POMDPs, which is not a good news. Okay. So for probabilistic automata, we were always interested in words accepted, so finite words and kind of reachability. For POMDPs, we can be interested in more elaborate objectives. So reachability, eventually some target state is reached. Safety, so always you stay out in the safe zone. Or Bucci, so infinitely often you visit a target state. And again, here we'd like to evaluate what is the best, or the supremum of probabilities that over all strategies, so over all news, that an objective is satisfied. So first, in order to evaluate this, then a very nice result is that there's no need to consider all strategies, especially that there are uncountably many. One can restrict to pure strategies, so to deterministic strategies. Because, deterministic strategies always subsume randomized ones. Okay? Okay, so as I said, all the undecidability results from probabilistic automata, they lead to POMDPs. But beyond that, we have more undecidability results. So for example, if we consider a Bucci condition, so repeated reachability, with positive probability, then this is undecidable, okay? Okay. Moreover, another example is the one of combined objectives. So if we want to guarantee two objectives at a time, so the first one is a Bucci objective with probability 1, and the second one is a safety objective with positive probability. Each of them is decidable when you do it separately, but if you want a strategy that combines both, then it becomes undecidable. Okay, so here was a proof idea for the first statement, but in the interest of time, I'll skip it, so you can find it. I can explain it later, if you're interested. Okay. So what about decidability? Well, the good news is that almost all decidable problems for probabilistic automata, they remain decidable for this larger class, which is POMDPs. So, for example, if you consider a safety objective that you want to guarantee with probability 1, then, okay, maybe I won't list all of them, but these three problems, they are decidable for POMDPs, and they can be decided in exponential time, and they are complete of that class. So what is the idea to get those X-time algorithm? So what we do is a power set construction in which you consider the beliefs, so the possible set of states the system is in, and then you compute some adequate fixed points on that structure, on that exponential structure. In the first and third problem, we can show that belief-based strategies are sufficient, but this is not the case for the second problem, for positive safety. And okay, maybe I can give this example. So here we see a model where we have 4 states, and the user or the agent cannot distinguish between state Q1 and Q2. So because of this cloud here. And we consider the goal of staying in Q0, Q1, Q2, so avoiding Q3 with positive probability. So, a way to ensure that is to start with A and then do B and alternate between A and B forever. So if we start here with A, then the system is here with probability half and here with probability half. So let's concentrate on this half probability. Then if we alternate between B and A, the B will automatically move there, because here B with probability 1 moves there. And then A will move to Q2 again with probability 1, and we can continue the alternation and stay within the safe area. Okay, the remaining probability half would lose, okay, I won't detail this, but would lose at some point. But still, if you alternate A and B forever, then you guarantee a positive probability to stay in the safe area, which is not the case for any belief-based strategy, because a belief-based strategy would either play A or B or any convex combination of the two, but because the distribution is fixed, eventually you'll end in Q3, almost surely. Okay, so I said most of the decidable problems for probabilistic automata remain decidable in this broader context. Well, there's still, up to my knowledge, one problem for which we don't know. So, and this is the one. So, this is a problem which is known to be decidable for probabilistic automata, but open for POMDPs. The question is whether there exists a strategy such that, under that strategy, there's a positive proportion of visits to the final state. So not only you want to visit the set of final state infinitely often, but with a positive proportion. And this happens with positive probability. So again, we know that this is decidable for probabilistic automata, but it's not known whether it can be extended to POMDPs. Okay, so I'd like to end my talk by a discussion on such models and problems. Maybe one lesson is that systems with probabilities, partial observation, and control are difficult to handle. So what did we see? We saw that most optimization problems are undecidable, so most decision problems associated with optimization problems are undecidable. And okay, of course, yeah, quite obviously, quantitative questions are very easily undecidable. But also we saw that some qualitative questions already are undecidable. And we also saw that I tried to convince you that the undecidability result was very robust. Okay, so these are not good news, but I think still that there is some hope. So maybe you're familiar to this way around. So what do we usually do when problems are undecidable? Well, there are several approaches. One of them is to restrict to decidable subclasses. And in the context of probabilistic automata and the value 1 problem, then again, Nathalie and others studied a class of league-tight probabilistic automata, so a subclass of probabilistic automata for which the problem is decidable. Another way is not to restrict the model, the class of models, but the class of strategies. So quite often if you restrict to finite memory strategies, even if you don't know a priori a bound on the memory size, then you obtain some decidability results. So I did not mention any references because there are lots of them. And another usual way around is to approximate. So if you don't know how to answer the problem precisely, then go for approximations. So in his PhD thesis, you propose some approximations techniques for POMDPs. Of course, because of the undecidability, okay, this is something I did not mention maybe, of the undecidability of even approximating the value of a probabilistic automaton, there will be no termination guarantees to that approximation scheme, but okay, maybe on some instances it will give some result. Okay, and so these are the usual things what one does when problems are undecidable, but here I'd like to discuss another alternative, which is discretization, but which is a bit different from the discretization or approximation here. And more precisely, the idea is to approximate continuous distributions by large discrete populations. So let me explain on a picture. So on the left you have a probabilistic automaton, and by the orange portions here, I wanted to represent a probability distribution. So we have 1/4 in the left state and 3/4 in the right state. Okay, and as I said, for probabilistic automata, if you're given a plan, a word, you can always compute after each step how is the probability mass distributed over the state. So you can compute such things. What if we approximate this distribution by a number of discrete elements? So for example, here I have 8 elements, and so I have 2 of them in the left state, a 4th, and 6 of them in the right state. Well, you could see that if you increase the number of those elements, so if you increase the size of the population, then somehow it approximates the continuous behavior. However, depending on how you interpret this, then what happens for large populations, if you increase the number of elements, is not, in the limit, is not what happens in the continuous case. So let me just detail this. So for example, here, if you want to, visit that state infinitely often with probability 1, then this is not feasible on that probabilistic automaton. Okay, maybe here you need to believe me, but if you fix here the number of an arbitrarily large but fixed number of elements, then it will be feasible there. Because intuitively what happens here is that each time A is played, all the copies here, all the elements here will stay there, and here approximately half of them will move to the right. So because this is discrete, at some point all the discrete probability mass will move to the right, and then you can do B and you can start again. Okay. So the fact that the limit behavior is not the continuous behavior can be seen as a drawback, because okay, it's not really approximating your original problem, but we can also see it as a very nice property, because then there is hope that some problems that are undecidable in the continuous semantics become decidable in this discretized semantics. So we can hope that this alternative semantics for probabilistic automata has more decidability than the natural one or historical one. Okay, thanks a lot.
Thank you very much.
Questions?
Yes.
See, earlier on you talked about robustness of undecidability, and maybe you talked about it here and I missed it, so apologies if I asked to repeat something, but if I were to say modify some of the probabilities at random or introduce noise into the system, this being the idea that this model is an approximation of reality, so that we shouldn't take the numbers in the model itself too carefully. Like, so how sensitive is undecidability to those types of modifications? Are you aware?
So so precisely if you like, even if I have less constraint than what you say, so I don't even assume I start with some probabilities and add some noise to the values, but I assume that I just have parameters. So I have P1, P2, and I want to know whether I can assign some evaluation to that parameter so that some property is satisfied, then this is still undecidable. I mean, depending on the property, but for properties I've discussed here. So, so it really means that, at least I interpret it as, it is not the case that the precise value of the probabilities induces undecidability. Even if you have some flexibility, it will still be undecidable.
But you stick to P1, P2, P3, P4 in this statement. You are allowed to choose them.
Yeah.
But once you've chosen them, they stay.
Yes, you're right. Yeah. Maybe you can give more detail because it's a result by Nathalie.
I mean, the result is robust in the following sense. You can find a class of automata for which whatever you put, whatever values you choose, the answer will be the same. So if you put P1, P2, P3, or P1 prime, P2 prime, P3 prime, then the answer is the same. So it doesn't even matter what the numbers are. It's just enough that they're here, and then the answer to your question would not depend on this. So the problem is robustly decidable in that sense.
But if you enter a state a second time, and then can you change from P1 to P prime 1? I think that was...
So you can change this. So
okay.
You can find a class in which it doesn't matter, for which it is still undecidable. Meaning that, for instance, if you want to go bigger than half, then you will have automata for which it's true for all different P's that you can choose.
Okay, but you can choose them dynamically, or?
No, not dynamically.
Okay.
So in Luce's undecidability result that you mentioned, that everybody and that including me were quite surprised,
he must construct an example. He must start from, this must be a reduction. So start from a non-decidable problem, show that you can construct an automaton for which the undecidability problem becomes acceptable. In that automaton, what are the probabilities?
You can use, I mean, the values, you can use just half and 1. 0, half, 1 is sufficient.
Can there be just 1/2, for example?
Yes. You can, this is undecidable, and also if you have a probabilistic automaton with a single, I think, correct me if I'm a single probabilistic branching, so just one state with a probabilistic branching, this is also undecidable. So it's very
robust.
Yeah, very robust and very difficult to identify a subclass which is meaningful and still has some good properties.
But the example that you showed us here, there seems to be a discontinuity. So
here? Yes.
Right.
If
you move to rational numbers, then suddenly a problem.
You mean rational? Yes, rational. You mean in the in the representation of the distribution? Yes. Yes. So it's not completely clear. Here it's something yet a bit different. So it's not only that I consider a rational approximation of those of this continuous distribution, but also, so maybe it was not very clear, but also, for example, if we start from there and apply A, then each such element, will with probability half independently with probability half loop or go right. So it's a bit different from discretizing with a given precision at each step, I think. I'm not sure it answers your question.
So maybe you can ask the question though, what questions aren't answered incorrectly by the approximation on the right-hand side? Maybe that. So I don't have them completely now. I can't tell you just now, but we can discuss later. So there are indeed some, for some problems, this approximation is, the limit is the answer that you get there. But okay, we can, yeah. But then we, if I remember correctly, we end up with problems that we know decidable here. And so, okay, maybe it's interesting, but it's less interesting than, I would say, than in that case.
Thank you very much. We'll take a break now and we'll resume around 4 o'clock. You hear the bell.